I wouldn't be too upset about not knowing that one. Okay, here we go. Here is where the fun begins.
This is
Okay.
where the fun begins.
Somebody asked me on Friday, well, what happens if it continues to cycle?
Forever.
Let's talk about that situation. Okay?
Was this the integral of e to the x gross on x minus e to the x squared?
Undefined.
Maybe.
Almost.
I'm
Okay.
Can our code word be uncultured swine?
Well, no one's gone.
Picasso.
Haley is.
Haley is.
Yeah.
I forgot.
Okay.
It's
Sorry,
Picasso.
Haley, I love you.
Uncultured
So
swine.
here we go. We have e to the x times sine of x. So we have a product, so that gives us maybe a hint that integration by parts could be an option. There is no room for u substitution, so that's really what we need to try. Okay, we have a product where u substitution is not going to work. Okay, well, we have an exponential and we have a trig function. We know that those both cycle through with derivatives and integrals. Would you agree? Okay. What was your alliteration from last time? Eilate. Okay. So we are going to let u equal the sine of x and dv equal e to the x dx. If we use Victoria's Eilate, trig comes before exponentials in our order of which we need to choose. Okay? Inverse trig. Yeah, which we're not going to do a whole lot with as far as these are concerned. Okay? Before I continue, do you see why we cannot use the tabular method?
Yeah.
Okay.
Why don't use that? I'd rather just do it 6 steps when I myself.
Okay. If we take the derivative of either one of those, it's not going to get to 0. Like, we have to have a polynomial to do that tabular method. So, okay. Let's work on this. If u is sine of x, then du is cosine of x. Thank you. And if dv is e to the x dx, yay, e to the x. So what do we have?
It's usually like plus minus.
We have u times v minus the integral of e to u. And you can't say that that wasn't expected, that we would have something that we would have to do again. Right? You were hoping? Okay. All right, so we have e to the x cosine of x dx inside of our integral here. So we're going to have to repeat this process. Okay, we are going to have to do integration by parts again. So I'm going to go ahead and do this in red now. So for this integral right here, what should we let u equal? So our dv would be e to the x dx, okay? And you can see how this is going to go similarly, right? Because of those patterns that we have with the integration and derivatives, okay? So if u is cosine of x, if u is cosine of x, du is negative sine x dx. And if dv is e to the x dx, then v is e to the x. Okay. All right, so what we have, we still have our e to the x sine of x. And now we're subtracting our new u times v minus the integral of v du.
Wait, but wouldn't it be minus if you put it in parentheses?
It would be addition because this is a negative sign of x.
Oh,
So we're subtracting the negative sign of x times e to the x dx. So I'm just going to go ahead and make that a positive. Okay. E to the x sine of x dx. Where are we going with this?
It's the same.
Oh, it's the same.
Thing. That's
It
really
is the
cool.
same thing.
So like e to the x sine of x.
So this is what we get to do. Okay? The integral of e to the x sine of x dx equals e to the x sine of x minus e to the x cosine of x minus the integral of e to the x sine of x. And what can we do if we have like terms?
Mine.
We can combine them. So here I have the integral of e to the x sine of x dx. And here I have the integral of e to the x sine of x dx. Well, negative, technically.
Add it over.
We can add it over. So that we have 2 integral e to the x sine of x.
so then you just divide it by 2.
Uh-huh.
That's fun.
Not as painful as you expected, right? So now I have 2 integral e to the x sine of x dx, so we can divide both sides by 2. Remembering that we still have that plus c since we found an indefinite integral. Usually you do that at the end, but this one kind of went. I mean, we did do it at the end, but typically we integrate this and we write our plus c, but instead we had to like combine like terms and divide. So let's just remember to put that plus c at the end. Okay. Is that kind of neat? Okay. If you don't have a polynomial, you cannot use the tabular method. But in this case, we are not going to get to an end. Like over here when we did number 16, you know, we couldn't use the tabular method even though we had a polynomial because of the log that we had in there. We made u our logarithm, but there is that nice relationship to where the integral that we subtracted was still something that we could do. With the cycling back and forth, we couldn't do that here. We had to combine like terms.
So like the acronym or whatever was like highlight. What was the A?
Algebra. Yeah, algebraic polynomials.
Yeah, it doesn't sound as good.
It's true. It's true. So inverse, trig, logarithms, algebraic polynomials, trig, and exponentials. Okay? And this would be for when we are choosing our u for the u dv. All right, 2 more problems I want to go through. What I'd like you to do is I'd like you to write down this problem and choose a u and dv, but then stop there. Okay. Write it down, choose what you think u and dv should be. I guess I should ask this. Can we use what makes you say, like, what sticks out to you that says no, it's not?
Well, there's an actual one, even though the x technically has an exponent or it's a polynomial, you still can't do it.
Okay, that logarithm kind of ruins it for us because we can't make that an integral step. Okay. Also, x to the 1/2 power would never get down to 0 because it's not. And that's why we say algebra instead of polynomial, because this technically isn't a polynomial. It's just more of an algebraic expression. It has a power, but it's not an integer power. Okay. So Hannah says we have that logarithm, which means we have to make it our u, correct? Okay. And so dv is x to the 1/2 dx. Okay. All right, so what does that make our du? 1 over x dx. And what does that make our v? Okay. So our integration by parts, u times v, minus the integral of v du. What happens when we take v and we multiply it by du? That would be 2/3 x to the 1/2 power. Are you in agreement? Okay, we have to divide. The exponent has a 1, so when we subtract, we get the 1/2 power. So we get 2/3 x to the 3/2 natural log of x minus, when we integrate, this becomes x to the 3/2. Well, that's kind of strange, isn't it? So 4/9. You're almost taking that same antiderivative, but with coefficient. Okay, I have one more example for you, and then you can start on your homework, which really shouldn't be too long of an assignment. So if you can get a lot of your homework done in class, you can just spend this evening going through problems to remind you of maybe our stuff from last week with section 1. So, since the beginning, since our problem of the day was a little bit of a struggle for us, let's have another chance at a similar problem. Okay, compare notes with your neighbor. April, what answer do you have? B. It has B. Annalie, why would April say B?
Because your D would be 6x squared. And
Okay, so the 6x squared is our du, so if we want our u, we have to go backwards, right? So our 2x cubed. Okay, how did we know that this was u? Okay, well, we have to have a u dv here, right? And we know that this is u times v, so the one that changed would be v, the one that stays the same would be u. Okay? All right, so at this point, get out your gold sheet and someone's book or take pictures of my book. I think that's kind of what most of us have done. But I want to give you the last 20 minutes of class to work on some problems. Ask me questions as necessary. And if you have questions for maybe the stuff from Wednesday, Thursday, you can ask me those at this time as well. Yeah, grab this.